Live. Welcome back again, Alan and Toby. We're going to follow up with some earlier talk that we had. We had a live stream, a great live stream a couple days ago, and there was a paper that you all brought up by, oops,
Ruyang Wang.
Riyang Wang. Yeah, sorry, I had my YouTube on. It was very distracting. Um, so, yeah, we want to talk about that paper. I did a quick look at it, and I think you guys have had a chance to review my thoughts. And let's discuss, what does it mean? What does it mean to us, and where do we go now?
Yeah, so we have a different interpretation than your reading, and we were actually we wanted to see if you wanted to do like a live reading of the paper with us because it's a pretty short paper. If we just kind of wanted to breeze through it, and we could see where we're different.
Keep going. I'm just stepping away to get my laptop, my iPad. You keep going.
Cool. So I'm gonna share the share screen here. Give me 1 second.
I might want to try and draw.
All right, cool. So I'll move this
Okay,
over here.
Alan's screen. We're gonna share it.
Yeah.
Okay. We're gonna just. What's the plan? We're just gonna read the whole thing.
Yeah, we'll just kind of read through and talk about each parts and what they mean because your take on it was that it was measuring that. So let me just basic. What you're saying here is that the fiber optic gyro is measuring the linear motion between itself right here and this loop on the track, right?
Between.
Sorry, I'll zoom in here. Give me 1 second.
It is measuring what now? It
So
is measuring.
Yeah, so you're kind of your
V.
your answer was that the fiber optic gyro that's on the conveyor is measuring the linear motion between the linear motion that's on the track loop, right? Because it's all connected to the same system, right?
It is measuring the difference between V and whatever the wheels are mounted to.
Okay, so okay, cool.
Measuring, it's literally is measuring V. Yeah.
Okay, so but your interpretation though is that it's measuring it relative to the other motion, right?
Well, it's
Like it's not relative to itself, right?
It's relative to the ground the conveyor is mounted on.
Okay. All right.
Right?
Cool. Yeah. So let's.
Do you guys agree with that statement or no?
So I don't. So you're so you're saying that it's all one speed, but then that would be relative to the ground that it's mounted on. Is that what you're saying? Or that it's measuring the difference between what the what this what the linear velocity would be going in this direction and this direction for the gyro.
It, I mean, you can see right there, right where your cursor is, it's measuring 4 pi V delta L divided by C lambda. So it's delta L is fixed. It's a constant for the loop. 4 pi is a constant, C is a constant, lambda is a constant. So the only variable in that whole thing is V. It's measuring V.
Okay. So relative to the stationary lab frame then, yeah?
Yes.
Okay. So if there is an observer on the lab frame should see no change in C?
Oh, right. Okay. C is a constant as expressed in that equation.
Okay. And for linear motion, C is also a constant, right?
C is a constant.
Okay.
Yeah.
So this should.
I mean, according to this paper, it is, right?
So in that regard, this should not detect any fringe shift pattern, right?
That is not correct because the fog, I'm going to call it a fog from now on, the fog is moving relative to its loop.
Moving relative to its loop. Okay.
The loop labeled optical fiber is not, it's spinning, but it isn't as a loop. The racetrack itself is not moving. Only the
fiber,
cable is.
yeah, the fiber is moving, and the gyro is moving in a motion with the fiber when that measurement is taken. It moves with the waveguide loop.
Right. The fiber's going around the racetrack, but the racetrack that it's going around is fixed to the lab frame.
Yes, and the fiber is as well.
The fiber is going around the racetrack. No, the fiber is spinning around those spools.
The fiber is moving with the linear motion of the racetrack, right? They're moving together.
The racetrack, okay, this is a little confusing to talk about. The racetrack, which I'm going to define as those two wheels on the end. The two wheels are bolted to the lab. They're not moving. They are spinning, but their hubs are still.
Okay.
Is that a good way to describe that?
Sure.
Okay. And so then the optical fiber, which is wound around those, is spinning through. It's going around the racetrack.
Well, it does one motion. What's being measured is the single motion of that forward momentum, right? When the fiber and the racetrack moves in that forward velocity motion, that's specifically what's being calculated is that motion relative to the speed of light.
Not relative to the speed of light. It's measured. Okay, say that again. Maybe I didn't understand you.
The way that it's calculated, there's nothing about being relative to the ground. That's not in the calculations. The calculations are showing that this particular velocity during this motion of the forward of the FOG and the forward movement of both sides of the racetrack, as we're calling it, that is all being measured. The change there is being measured relative to the speed of light.
No.
Okay.
It is measured as a fraction of the speed of light.
So there's
no minus c, right? You see this equation right here. It's on your screen. 4 pi v delta L divided by c lambda.
Yeah, so that part specifically talks about the conveyor portion.
That's what we're measuring.
Well, no, scroll down, because that specifically is about you have pi in there, right? So that's not the linear portion.
The effective length, the phase difference, right? The phase difference, theta, and actually says is not that, but is the longer form is on the next page.
Yeah, where I think that's where he goes into the linear derivation.
But the only difference there is a cosine on it. That's it. Right. The only difference is he's added the cosine theta, right?
Yeah.
Right. So there is no minus c or v minus c or c minus v in this equation. There is no relative velocity compared to c. There is only a ratio of v divided by c.
Yeah, so why would you get a variance with c based on that?
You don't get a variance in c. You get variance in v.
But
right, you get a variance in delta theta or delta phi, right? Delta phi is what he's calculating. The phase difference is he's calling it delta phi.
So your assertion is that the relative motion is only relative to what?
It is v relative to the lab frame.
And what is your how are you measuring your relation to the lab frame?
How am I measuring that?
Yeah, how are you attaching yourself to
That's
reality?
literally what v is. The conveyor belt is sitting in the lab, and the wheels are in the lab. We good on that? We agree with that?
Yeah, and the FOG is in the lab.
And the FOG is, well, it's in the lab, but it's moving. Unlike the wheels and the conveyor belt itself,
it's moving with the
conveyor. It is moving relative to the lab because of the conveyor belt.
It's moving with the conveyor. It's in the same lab frame.
Well, in the lab frame, it has velocity v. The FOG does.
Okay.
Moving in that diagram, moving to the left. Moving to the left at speed v.
Okay, yeah.
That is the velocity of the FOG relative to the lab.
How are you relative to the lab?
Interesting.
Based on what?
Well, that's just basic Newtonian, Galilean determination of what velocity
So
means.
are you claiming that you could measure the same velocity without the light?
The light is what we're using as the measurement technique in this experiment.
Well, we're using the phase shift, right?
Yes.
Okay. And so what is that what's causing that phase shift?
Can we back up and do the V first? Because it seems like we're confused about what V is.
I don't think we are.
Okay.
We're talking about the FOG and the fiber, right?
The FOG is moving to the left with speed V.
Yes, and same with both sides of the racetrack.
But the wheels are not moving to the left. They are spinning.
But where the calculation is not calculating
can
the
we
wheels.
agree to that before we move on? Can we just agree that that's what's happening?
Sorry, recap. Say it again. Sorry.
The FOG is moving linearly to the left at speed V.
Yes.
Compared to the floor, right? The floor is not moving.
But the floor isn't in the equation.
It's not drawn. It's just assumed, right? It's just assumed that we understand the lab is holding still. We're not doing this on the back of a truck or something, right?
So then is your position that we would take a geometrical position at the center of this outside of the lab frame and do a Lorentz transform based on that?
No, we don't need Lorentz transforms for any of this.
I mean, okay.
I don't think the Lorentz transform appears in this paper.
No, it doesn't. This is purely classical. There's nothing relativistic in this entire paper.
That's right. You don't need it.
Yeah, so I'm trying to understand your position. You're saying it's relative to the ground, but then how are you even asserting a relationship to the ground?
Well, the conveyor belt is sitting on a table or something, right?
But how is that related to the motion of the fiber and of the FOG? You have an absolute velocity of those components, right? So
there's no such thing as absolute velocity. All velocity is relative. And this goes all the way back to Galileo. We're not talking about Einstein. We're talking about classical, right? Classical physics like you learn in high school. When you drive in your car, you're going 55 miles per hour. Not compared to the person next to you.
I understand.
Compared to the ground.
I understand.
So V is relative to something.
Yes.
So the V in this diagram is relative to the lab, right?
So
no,
he's not making any mention of the lab though in the equations, because when you read this paper, what you find out, he explicitly says that it's not
right.
that it's not relative to anything. It's not relative to any refractive index. It's not relative.
I'm sorry. You go ahead. He doesn't say that it's relative to the lab. Do you guys think that it's relative to something other than the lab?
Yeah, relative to the ether. Because he actually
how did
went.
he get hold of this ether? Where is the ether that he measured?
Okay, so this phase difference here is produced by a variance in C. That's what they're measuring here.
But he doesn't say that.
It doesn't matter if that's what he's saying. That's what he's doing. And then he later went and patented technology based off of this, dude.
Okay.
Hold on one second. That measures absolute motion based off of these experiments. Because right here, it's like, okay, maybe there's some absolute, maybe it's measuring relative motion between the FOG here and the racetrack or whatever, right? But in this configuration here, there's no rotation. This is just the linear motion here, and it's only detecting the length or the only part of the phase difference that's showing up is the length of what's in motion and the motion of the source here. So it's
Okay.
detecting motion next to nothing. It's relative to the preferred frame, he calls it in this patent. Like it's like come on, the old preferred frame. Like
It's in the preferred frame. Great. And it just so happens that his lab was built on the preferred frame.
Yes. So how is
Okay,
he
awesome. I mean,
how is he maintaining well, hold on. What is his measurement of how is he getting anything outside of the light? There is no measurement of a stationary frame outside of the velocities of the waveguide loop and the FOG on the conveyor, right? So how are you ad hocing in a stationary frame outside of the reference frame?
yeah, it seems like we really need to go back. We need to wind way, way back and talk about what is a reference frame.
Well, hold on. Can you try to just answer my question instead?
Because the question is, where did I come up with that it's in the lab reference frame?
No, I'm saying how are you asserting that? How are you taking the lab frame, a stationary frame, outside of the reference frame? Because the reference frame is a state of velocity, right? A state of motion with as we just went over, and so we're showing that the calculations here are in relation to something outside of that reference frame because it's working off of
No.
a preferred. He says the words preferred frame. So where are you
Where
drawing?
does he say that?
Where else are you drawing a connection to a preferred frame other than through the velocity of light?
We don't have any such. I didn't notice any
And
mention
the
of the word
relative
preferred
relative
frame.
velocity of the actual.
Can you please just do Control F, preferred?
so in this paper, he goes over right here. Hold on, I'm gonna bring it up.
Show me where he mentions the word preferred frame in this paper.
He doesn't say preferred frame in this paper.
Okay.
But listen. Hold on one second.
Look, we're talking about this paper.
Hold on. I know, but listen, I'm going to explain what we're talking about here. He eliminates what you're saying as a possibility, and then he went and patented technology based off of this experiment at the same time, where he explicitly explains what the relevance is here. He went
in some other paper. And some other, you're referring to some other paper.
Not in just some other
and
paper.
Show it to me in the words.
Bro.
I don't want to hear anything else that's not in the words here.
Okay. All right. Let's read the paper. Let's see. Linear motion of the
but I seriously think we need to go back and talk about what is a reference frame, what does velocity mean, because the words that you're saying don't match what I'm saying. I think we have a disconnect in communication about what I mean when I say the FOG is moving relative to the lab.
Okay.
I mean, that's
okay.
We really need to back up. If that's a confusing statement, then we really should talk about that.
All right, cool. So this general conclusion includes the Sagnac effect for a rotational case. The finding also suggests a new fiber optic linear motion for having a nanoscale sensitivity, which is much more sensitive than any existing linear motion detector. This linear motion sensor can be applied to accelerometers in navigation and seismology, which he later went and patented based off of a preferred frame. Based off of a preferred frame.
No, actually, he
doesn't say
filed the
preferred
preliminary patent work before he even got to this experiment.
He does not say the words.
It was even before this.
Yeah, it was after his 2003 experiments.
The words preferred frame don't appear.
I'm explaining to you the difference in what you're not getting here. Okay.
Well, yes, but the part that you're telling me that I'm not getting is not in the paper. So where are you guys getting that from? Some other place.
The relative motion that you're trying to attribute, though, doesn't exist in this paper. As you read it, he eliminates that possibility, and then later patents technology based on.
Where does he eliminate that? Just show me that.
Our experiments are different from the Fizeau type experiment of the drag experiment of a moving media. The Fizeau experiment, there is relative motion between the light path and the medium of the glass. The results of the Fizeau experiment is dependent on the refractive index on the medium and the drag coefficient is 0 where the refractive index is 1. In our experiment, the FOG, there is no relational motion between the light path and the medium, the fiber optic, the glass fiber or the air core fiber. Okay, there's no.
Agreed.
It's not detecting relative motion to anything like you're saying. It only.
That isn't what he just said. He did not just say there's no relative motion. Read it again.
There is no relative motion between the light path and the glass medium.
He doesn't say there's no relative motion, period.
It's detecting the phase difference. It's detecting the
He's
velocity
saying
based off of the phase difference off of the speed of light, bro. Like,
he's
that's it.
saying very clearly here, right? Look at the words. He's saying there is no relative motion between the light path and the medium. The medium is the glass fiber,
Mhm.
and the light path is that racetrack, right?
Yes.
So he's saying that the racetrack is going around, and that's not what he's measuring. He's not measuring a difference in the speed of the glass. He's measuring the FOG moving relative to the racetrack. That is what he's measuring, which is different from this other dude's experiment.
The
Right? The other dude moved a piece of glass through the apparatus.
I get that.
In this case, we're moving, the apparatus is moving.
Only the linear motion is getting detected here.
Agreed.
I have like maybe a straightforward question that maybe could help us all to understand each other better.
Mhm.
So you provided the paper for just a general response to the Sagnac effect in the light of a relativistic framework. I can't remember the exact name of it.
Do you mean the Tartaglia, maybe? Sagnac effect and pure
I think that's
geometry?
it.
Yes, that one.
Uh-huh.
And so in that paper, basically, there's like what's drawn out there is you have two interpretations, right? You have the classical interpretation of the Sagnac effect, which would have to acknowledge a shift in the velocity of c, right? Correct?
No, it does not. It's this same thing. There's no shift in the velocity of c ever mentioned in this paper. There's none needed for Sagnac. Sagnac, sorry. There's none mentioned.
So then what is
either
being measured in the phase shift?
in Tartaglia. The relative velocity, like this diagram you have on your screen right now, makes it very, very clear. The top piece of glass is moving to the left. Agreed?
Mm-hmm.
The
Yes.
bottom piece of glass is not moving to the left. They are at different speeds. Yeah?
Oh my God, I thought that one was moving too.
The top piece of glass is moving,
Okay.
indicated
I
with the
see.
delta L.
Yeah, I see. So
And the bottom where the coupler is at is not moving to the left at V.
So in that equation though, the only part that's being measured is the linear motion. It's not referencing the stationary part. It's only the total length of this loop.
That is
here. I mean this right here.
That is correct. And
So-
just like when I say I'm driving at 50 miles per hour, I mean 50 miles per hour relative to the ground. I just don't feel compelled to say that because everyone knows what I'm talking about. Same thing here. There's a V indicated on the top bar, and he didn't feel the need to write a 0 on the bottom bar.
Well, maybe we should just stick, since I feel like we're kind of we're talking over each other here right now because we're going deep into the linear stuff and these particular experiments. But I think maybe before we do that, we need to all get on the same page about just the Sagnac effect, right?
Okay, yeah, you want to go back and just
Yeah.
talk Sagnac, the original Sagnac effect?
Yep.
Well,
I mean,
yeah.
this one's actually easier. It's ironic.
Well, so I want to go back to kind of what I was trying to pick apart earlier, because what I was trying to say earlier is the phase shift detected in the Sagnac effect shows, I mean, it's related to the velocity of light through the medium. I don't understand how else you explain it other than with a Lorentz transform, where you have to take a convenient geometric position to then do geometry to explain everything.
That's interesting. The Tartaglia paper that I sent, and you had kind of complained that it used the Lorentz transform. If we looked at that one again, you'll find that he does state the Lorentz transform, but he also states...
Yeah, as a relativistic explanation, because in the classical explanation...
No, you didn't read it. You saw that and you stopped.
We read it, trust me.
Okay, well, let me explain. He says that, and then he also says, but in these cases, V is much, much smaller than C. So we can disregard all of that. And then he just does it in classical. There is no relativistic effect involved. He discounts the relativistic effect and just moves on classical.
So are you unwilling to accept that in the classical interpretation of these experiments that it's C plus V?
In the classical interpretation of these things, it could be C plus V, but we have no way to determine that, because it doesn't matter.
Because if you jump out of the lab frame, you could have infinite possibilities.
I don't know what you mean by that, but these experiments don't show any absolute frame bias or preference whatsoever, because the Sagnac, right? Sagnac just goes around in a circle, right?
Yeah,
or back and
so
forth, or in a diamond, or whatever.
right. And Sagnac's interpretation was that it was that the motion of the rotating disc created its own ether drift that was proportional to the velocity of that disc, because that's why there's a first order dependence on the rotation. That's what his interpretation was. So he was saying that
maybe.
It says,
but he has no reason to think that. I mean, he
listen,
can just make that up if he wants.
I mean, that's how the classical math is shown to work out.
That's what C plus V is. That's like the mechanism for it. So he's saying that the motion generates a vortex ring, right? That causes the variance in C proportional to the motion.
Or we could just say that it's C plus V going to the left and C minus V going to the right. Okay, right? We can say that. This is the classical
we can just say that.
Interpretation.
Okay.
The classical ether interpretation. We don't need to make vortices or anything complicated. It's very, very simple. C plus V going one way, C minus V going the other. That's it.
Hold on. The only reason I brought up the actual mechanisms for it is because you were acting kind of like there was no possible way that the interpretation was that this was C plus V. So it's like now that we're on the same page of the original interpretation of Sagnac, we can proceed forward, because this is...
No, I'm telling you, you guys are off track. The original interpretation is just that it's perfectly normal under regular classical mechanics. It doesn't need any advanced, complicated explanation.
But you just submitted C plus V and C minus V. So
Sagnac we have 100% compatible with C plus V and C minus V.
Okay,
it just works.
Okay, so we have two choices, right? We can accept a classical interpretation that there's a C plus V and a C minus V happening, or what do we need to do?
Or we could say that C was constant and it was just C and C.
Aha, and then we can take a geometrically assumptive position and make calculations based off of a Lorentz transform.
No, we don't need it.
Don't you find it kind of odd that you can't even explain a local Sagnac effect without invoking Lorentz transform?
I find it ironic that despite the fact that I've told you this several times, you still pretend that I'm taking a position that I'm not taking. So either you're not listening to me, or you're just doing something performative here.
I'm not trying to do anything performative, but I'm just saying, you just admitted it's C plus V or C minus V.
No, I said we could, I did not say that, right? I said we could take the position that it's C plus V and C minus V. The Sagnac effect is 100% compatible with that. We don't need anything more complicated than that. Totally works. Okay, can we just stick a period on that and not argue about it? Sagnac effect under classical dynamics needs no further explanation.
Sure.
Okay. Under special relativity, we would have to somehow have CV constant as it was going both ways around the loop. It's not C plus V and C minus V. And guess what? That's also 100% compatible with the Sagnac effect.
So in this equation,
the Sagnac experiment cannot discriminate between classical dynamics and Einstein.
Okay.
It's incapable of it. So it tells us nothing.
Yeah, so C plus V is the variable then, right?
What? Is that what I said?
In classical mechanics, like that would be that's the difference for the Sagnac effect,
The
right?
Sagnac
C plus V, C
effect.
minus V, that's the variable that causes the friend shift, right?
Sure.
The variance, the
Okay. I
variance in
mean, in a
C.
way, yeah.
Yeah,
Yeah.
because otherwise the friend shift, because if it wasn't, then if C were constant then in that interpretation, right, then it couldn't produce a fringe, right? So logically,
No,
C
that's
plus V.
incorrect.
Oh, Doppler frequency.
Look, in the
Or whatever.
Sagnac effect, the
Listen.
device is spinning. Okay?
I get
The
you,
device
man. I
is
get you.
spinning. And if the device is spinning, moving with the spin is a longer path than moving against the spin. Can we all agree that that's a fact? If you're chasing the spin, you have to go farther than if you're going against the spin.
Sure.
So it should take you longer to go with the spin than it takes you to go against the spin.
Okay.
All right. And so if we take two racers on a rotating track and they race in opposite directions, right? Then when they meet back up, the one that had to go with the spin had to go longer than the one who's going against the spin.
So I want to just make sure I'm on the same page here. So
Okay.
You're talking about that the distance somehow changed that the light is traveling.
Yes.
How is that not entirely dependent upon the speed of the light?
Yeah, that's a good, really good question. Really good question. We could say the time that they traveled. Perhaps distance is the wrong word. It takes longer to travel the same distance, we could say.
So the speed of light?
It takes longer to travel the
So is
same.
the speed of light changing then?
That's a really good way of seeing it, but no, that's not correct.
So what is the?
Oh, we almost were correct, dude.
What is the calculation of speed?
What is the calculations of distance divided by time? Yeah, that's right. Yeah.
And so what is the fringe shift measuring?
Did you remember? We should probably back up a little because we're losing a little something here. The distance is literally longer on the one direction than the other. And why is that? Did you remember that the device is spinning?
Well, I mean, the
device is literally spinning, right?
The distance is not literally longer, though. It's just a motion.
Yes, no, it is.
It's a parallel motion. It's a linear motion.
No, the distance is literally longer because the device is spinning, and they met up back at the same spot on the circle, but the circle's turned. So that's not the same spot in an outside reference frame, right? In a non-rotating reference frame.
It's just linear motion, man. It's one linear motion there that the FOG makes. It's not going in a circle around the whole conveyor. The waveguide loop, it's just one little section. It's just one little motion of the waveguide loop that's being measured here.
Are we talking about Sagnac or this thing?
Well, in this case, we're talking about this thing, I'm saying.
Okay, you want to talk about this thing?
We can go back to Sagnac if that's easier to talk about.
This thing is actually easier, in my opinion.
Okay.
Okay, the light comes out of the FOG. It goes around the racetrack and it returns to the FOG.
Yes.
Did that take time? Was there time involved?
Yes.
During that time, did the FOG move?
Yes.
So the net distance that the light traveled is the amount that the fog moved divided by that time.
But you're missing the point because the whole conveyor moved. So the optical cable itself, the length of the optical cable did not change whatsoever. It stayed the same length.
Right.
So the distance.
So it's not the length of the cable that matters. It is the distance the light travels from start to finish, not the medium, as he says here, not the medium it's going through. but absolute space.
Absolute space. Isn't that interesting?
That's right. Yeah.
Yeah. And so
Uh-huh.
if you're calculating a velocity based off of absolute space, how are you going to say that absolute? Do you get what I'm saying? You're stepping into a preferred frame. You're stepping into, yeah.
I haven't though. I mean, I did use the word absolute, which sounds like a preferred frame thing.
I mean,
I
it's
just
an absolute
mean
frame that you'd have to invoke in that case,
no.
relative to the background of what the light's propagating through.
Right. I have not invoked any special relativity. I'm purely doing this classical, right?
Yeah, and so then we get C plus V and C minus V.
Once again, that's not in this paper anywhere. Is there any C plus V equation anywhere in this paper?
No, but he's showing that you can detect linear motion with a fringe shift.
And I'm saying, yeah, classical dynamics says you can. And there's just there's not even any need to get into special relativity. We haven't even invoked special relativity.
But you already admitted that classical mechanics admits that it's C plus V and C minus V. For some reason, you just don't want to apply that to this paper, which I'm not really, that seems really incongruent to me.
Why do you assume it? Unless
because we're talking about the Sagnac effect, are we not?
Unless this paper can demonstrate that C plus V, C minus V is relevant to this answer, then it's like saying the sky is not blue. I mean, it's just completely unrelated, right? This paper makes no mention of C plus V, C minus V. There's nothing in this paper that can support C plus V, C minus V.
But you do admit that it's measuring a classical Sagnac effect in the same way that a classical Sagnac device would measure it, correct?
Yes.
So it's C plus V and C minus V.
No.
Why not? Why is it different here than in a classical Sagnac experiment?
It's okay. There's two questions there. The one you asked is, why is this different? It's different because this is not measuring a rotation, but instead a differential velocity. And you'll see that in his patent. He's measuring, he wants to use it for like a seismometer. He wants to measure
for a speedometer.
A seismometer.
No, a speedometer.
You'd have to have a gloriously long fiber optic cable to pull that off.
Well, his model's standalone unit.
I mean, we can pull up the patent real quick.
If you want to, I haven't looked at that. You asked that, but then there's a central tenet here that I've said several times, and I don't know why it's not getting through. I'm going to say it once more, and I want you to say it back to me to prove that you are hearing the words that come out of my mouth. Mm-hmm. The Sagnac effect cannot discriminate between classical and Einstein relativity. It cannot tell the difference.
Yeah,
repeat that back to me.
It can tell the difference.
It cannot tell the difference.
Yeah, it was done in deformed printer 1920. Can you hear me? Is my mic on?
I do, Alan. You're just telling me I'm wrong.
Yeah, in 1942, the special relativity predictions weren't matched for the experiment that was done.
That's not true, sir.
Okay.
It was before Sagnac even did the experiment. The math was shown that it doesn't matter. The results are the same under special relativity as they are under classical. This was shown in like 1911, no, before that, I don't know. Long time ago.
So let me give you a little history lesson real quick. Then my dude.
Fact.
I need to step away really quick. I'm sorry.
Yeah, you're good. So Einstein says that any closed polygonal circuit completing uniform rotation is defined as an inertial frame. You agree?
No.
Okay. Well, let's pull it up in the paper and read it directly.
No, we're not going. We're not going to another paper. We're on this one paper because you guys are going to pull us off into all kinds of different directions.
It's not all kinds of different directions, bro. You're saying all kinds of craziness to invoke a relativistic explanation. Do you understand that Sagnac?
No, I did not. Listen to me for once, Alan. Just listen for a second.
For once, bro.
This experiment does not require special relativity at all. There is no mention of it There's no need for it. It doesn't even mention it.
It wouldn't mention a model that it falsifies.
It no, it would have to. It would literally have to mention how it falsifies it in order to falsify it. You can't falsify a model without even explaining what that model is, right?
Listen, the classical interpretation of the Sagnac effect is C plus V. That's why Sagnac published his paper that in an inertial frame, C plus V falsifies special relativity, because Einstein, in his 1905 paper, defined a closed polygonal circuit completing uniform rotation as an inertial frame. So basically, in his thought experiment, what he was describing, he said, basically, he described what would be the equivalent of now an atomic clock on a satellite orbiting around the equator. So he considers that an inertial frame. Okay.
Okay.
That's
well,
why.
Go ahead.
1 second. That's why Sagnac in 1913 said, "My uniformly rotating platform, blah blah blah," right? Because he showed a C plus V in what Einstein, in his own theory, considered an inertial frame. And then it took until 1917 for a special relativity derivation to be provided, and that required them to transform to the center of the rotating platform, et cetera, et cetera. And then 1 second, and they weren't really happy with that. So Paul Leveau came in 1918 using general relativity, and they said, okay, well, it's a rotating device, so we'll treat it as acceleration. Therefore, we can treat it as its equivalent to a gravitational field generating little pockets of length contraction and time dilation. Like, they literally explain it in that regard to maintain the constancy of C. So when you get into that level of it, like the interpretation of C plus V is much simpler. And then when you said
Cool.
that, okay, go ahead.
I don't want to argue with dead people. I will take my position, and I ask you guys to take your position. Okay.
Yeah.
And I want to review this paper, and I want to understand it in terms of basic concepts, and not argue about things that jump forward of other stuff. So step one, velocity is relative to something. Are we okay with that?
To a preferred frame, I'd say.
Do you have access to said preferred frame? Can you measure said preferred frame?
Yes,
in this experiment. In this experiment, what is the preferred frame?
What's the measure? What's the variance in C being measured against?
There is no variance in C being measured by this experiment.
What?
C is literally a constant in that equation.
In your interpretation of the fringe shift, what's being caused here? How's the fringe being caused?
V.
So V
is the variable. Look at your diagram. Look at your diagram, guys.
So it's literally C plus
scroll
V.
Up just a little bit. Scroll up just a little bit more.
Yeah.
Down. Show this diagram that's just off the bottom of the screen. Show the whole diagram. What is the dependent and what is the independent variable, please?
Let's see. Where are we at here? This diagram?
Yes.
Okay. So your dependents are, your dependents are 4 pi VL over C squared.
C lambda, but yeah.
Yeah, C lambda, sorry.
And it's labeled, it's actually labeled on the bottom diagram there, right?
Where?
Bottom of the diagram, it's got a label for its x-axis.
X-axis. Read it off. I don't see it. Just read it off.
Speed times fiber length.
Speed times fiber length. Okay, so the length of the device.
So
right, and the speed, and then relative to what?
The speed times the fiber length is the independent variable. Can we agree?
Yes.
And the phase difference is the dependent.
Yes.
Cool. Where is C in that?
It's relational to V.
So it's V divided by C is what we're calling speed.
But you said yourself that the distance is changing, and we already discussed that C is going to be relative to that distance change.
I don't understand how you jumped there from what I just said.
What is
the
C?
word speed? Can we just start with just the word speed? He means v divided by c.
V divided by C, C being
a constant.
So what is C? C is the speed of light, correct?
Yes.
And what is speed?
Distance divided by time.
Okay. And if we're making changes to, how else are you explaining the fringe shift other than with distance?
With distance. The fog moved. It moved by speed v. The fog moved by speed v.
And the only way to detect that, is with C. That's the only reference you have.
It's in reference to C, bro.
We've measured speed since the dawn of time, right?
You have to have a reference, though.
The table, it's on a conveyor belt that is calibrated to be moving at a speed v. This is literally the independent variable. He's changing v on purpose.
And that affects the fringe shift.
Right.
And you explained that because what we're measuring is a fluctuation in laser paths, right? We're measuring a phase difference.
Yes.
That should not exist.
Why should it not exist?
If C is constant.
That is not correct.
Why not?
Okay. If C through glass is constant, right? If the speed of light going through the fiber optic cable is constant, we would not get a fringe shift.
Okay, so
right?
So you can measure. So you're saying that you can measure V in this using this setup, right? Against the speed of light. Okay. So then why did Michelson-Morley detect Earth's orbital velocity?
That's a different setup.
They're all the same. They all detect sidereal rotation.
They're all detecting a fringe shift.
They all detect a fringe shift that does the same thing. It's all the same variance.
Yeah, I'm really struggling with this. It's amazing to me.
No, because you're picking and choosing.
It's very, very simple. I am not picking and choosing. It is very simple. And you guys just really want to jump to an answer that isn't here.
Dude.
It's really amazing. I mean, can we just go through the math? Can we just like take it step by step and see how?
I don't think it's a mathematical.
This is actually inconsistent with classical dynamics, but it's consistent with special relativity.
Once you ever apply a Lorentz transform, yeah.
No, you don't need it.
So that is C plus V and C minus V.
No.
You can't have it both ways. You can't have it be C plus V and C minus V and also say it's relativistic.
Okay, let's try it. Can we just try it both ways? Can
we
just try
it? Then the Earth's not moving.
Can we literally just try this?
I don't get what you mean, but sure, yeah, sure. Go ahead, explain.
Can I write on this like that? Okay. The light comes out of the. Let's go back to the diagram of the thing. You know what? The easier diagram. Let's go to the bottom diagram. Can we do that first? It's on the next page, I think.
He's talking about the slackline experiment.
Oh, I'm sorry.
He's busy. He's busy with some chat.
I was reading chat.
Okay, that one. All right. Here's the deal. Light's going to come out of the source. It's going to go up the loop both directions, right? Part of the line, the fiber optic cable is moving to the left at speed v. Okay?
Yeah.
All right. So under classical C plus V, right? Then as the light moves across delta L from left to right, it's moving at effectively C minus V.
Yep.
And the right to left is moving at C plus V.
Yep.
So the times it takes to arrive back at the couplers does not match.
Yes.
Okay, so that's the classical explanation. We have had to accept, though, that the speed of light through a moving medium is not dependent on the speed of the medium. We've had to accept that, right? Because otherwise, because we
Based
didn't
on
change
what?
the length of the cable, we just moved the cable.
Yeah.
Okay. So under the, we'll call that the classical, and we'll stick a pin in it. Cool?
Okay. Okay.
Okay. Now let's do it under relativistic. So the light goes around and it's heading in the direction of the cable, right? And the light is going opposite directions around the cable, right? Just like it was. And it's literally going to take longer if the cable is moving in the direction of the motion.
That movement is in relation to what, though?
The V is related to the coupler. The V is greater than the speed of the coupler.
But okay, so then the fiber cable length didn't change. Still the same length of cable.
But we already accepted that the speed of light isn't relative to its medium. You had to accept that for the classical version. Remember?
Okay, I see where you're going.
It's
with
moving
this.
through
So, yeah.
space.
Okay, I see where you're going with. I see
The
your
space
point.
that
Okay.
it moves through is longer, whether we're
So then-
relativistic or not.
I see where you're going with this. Okay, so then you would only be satisfied if we did have like a de Forum-Pruner version of this. Was what would satisfy you in that case then?
A what version? I'm not familiar with that term.
If we could then take the fringe shift and measure it outside of the reference frame.
Like measure it outside of the
Okay.
the parts that's moving, like that would.
Beautiful. So let's take this whole thing and let's put it on the back of a truck or an airplane or something, and let's haul ass. Right. So that V at the top is now V plus truck speed. Let's call truck speed what? S.
Mm-hmm.
So V at the top is V plus S, and the speed of the coupler is just S. Right? We'll put the whole thing on a truck and we'll haul ass and try it again.
Yeah, so wouldn't that be crazy if you could measure your absolute speed with that?
Just check the math with me, right? Let's check the math. As we go across the left to right, across the top, we're going at speed like C plus V plus S. And if we're going the other direction, it's C minus V minus S. S drops out. It doesn't freaking matter whether we're classical or not. It just doesn't matter.
Interestingly, actually, I think it would matter depending on whether you're driving east to west or north to south because of the either one, but that's a totally different topic.
Well, that would be a different topic. But if we just take the classical, right? The speed of the coupler, or the speed of whatever this thing is bolted to, is literally not measurable by this device.
So you say.
It is. You just agreed. And did I make a mistake?
Well, no, I was actually thinking of something different. My bad. I'm thinking of atomic clocks, which is different. So in this case, we're measuring specific motion. But yeah, I mean, I see your point of view. That's why I say maybe if we could measure the shift outside of the reference frame, maybe that would satisfy you. Which maybe you should look at the Forum-Pruner. Because that specifically is measuring its rotational Sagnac effect, but it does measure it outside of the reference frame.
We can go on to that topic next if you choose, but first I want to finish this one and call it done, because I think we just decided this paper does not support any of your claims and needs to just be removed from your list of supporting
No, I mean
evidence.
it's showing a classical interpretation that not just the rotational motion. Let's just stick to the classical framework. Not just the rotational motion is relevant for the Sagnac effect, but also linear motion.
That's true. That is absolutely true, and I agree with that statement.
Okay.
But what it does not show is any kind of preferred frame of reference. It does not show C plus V. It
does show C plus V relative to that reference frame.
It can't support that. It does not show C plus V. As we just described, it's C plus V one way, C minus V the other way, right? And those V's, they just drop out. They're not relevant. The relevant portion is the difference between how much the cable moves relative to the coupler. That's the only part that matters.
But that only works with a preferred background frame.
No, it works we just did it on the truck, and the truck didn't have any impact on the result, which tells us it is not only relevant to some absolute reference frame, even under classical, like no relativity at all.
What were you going to say, Alan?
I was going to say, I had a comment come in that says, by the way, a speedometer in a car measures the velocity of the car relative to the ground by using the rotation of the wheels, and weighing measures V, or the velocity of the conveyor relative to the lab using the speed of light. So the analogy that was used earlier of the car using a speedometer not needing a state of ground speed is 0 is a total red herring.
Oh, did anyone say that? Did anyone? I don't think any of us said anything like that.
I said something like that. And I think what your commenter said sounds right. It sounds right. Yeah.
So
I don't know why that's a red herring. Anyway, go ahead.
We're back at C plus V then, man.
So he needs.
How did you come away with all of that and say C plus V? There is literally no C plus V anywhere in this paper. And if you add the C plus V, you get the C plus V one way, you get C minus V the other way. It cancels it out, right? There is no effect.
You said that the speedometer doesn't need to state the ground speed being 0. Is what he said.
Because we assume it, right? We all assume that.
Okay.
Right? So when the V, I'm talking about the V in this diagram, right? The V in this diagram is not measured. It is the input, right? The measured is the fringe shift, right? The independent variable, the lab, the experimenter turns his dial to make V a calibrated speed. Well, we all agree to that, certainly, right?
Mm-hmm.
Yeah.
Yeah, and that's the speed of the conveyor belt. The conveyor belt is sitting on what? The lab table, right?
Well, in this particular one, but he also has an air conveyor where
it's not
attached to anything. And it's
cool, but I mean, he's calibrated V relative to himself, to his lab, to, right?
Sure.
That's not controversial. And he measured a fringe shift. Yes, he does, because not the length of cable. The length of cable does not change in these experiments, and I think we all agree on that. It is the amount of space that the light travels through that changes, right? Because the cable itself is being moved.
Sorry, say that again.
What changes in this experiment is not the length of the cable. The length of the cable is fixed.
Right.
So when he says delta L, right, that's not the length of the cable. It's the length of space that the light has to go through.
Oh, that's not the fixed length of the cable?
I don't think so.
I'm pretty sure he says that
when he says delta L,
he defines, so delta L is the effective length of the cable. Okay, yeah, so you're right. The effective length would be the total of the linear motion, right?
Well, I don't know. No, maybe delta L is just the length of the cable in his equation because he's got it multiplied times V there.
The effective length. Okay, so yeah, so it is just.
So it is just the length of the cable.
Yeah.
So delta L is the length. So it's delta L times V.
Yeah. So fixing it that way, wouldn't the natural interpretation be the variance in C though?
The natural interpretation that we can make without invoking any assumptions at all is that the speed of the light going through the cable is not constant with respect to the cable. That movement of the cable affects how long it takes to go through there.
Right.
I guess I said that really badly. I said that really badly.
Well,
It's
yeah,
the
but if
space that it goes through that matters, not the glass that it goes through. It's not how much glass it goes through. It's how much space it goes through.
right, but if you're measuring V with C, then that can only be done with V or C plus V, or C minus V, right?
It turns out, no, that's not the only way.
I mean, I guess, bro.
That is a way to do it.
I guess we're
a
just
way to do it.
hey, I guess we're just at a philosophical impasse then. Like I
Well,
can see your interpretation now. It makes a lot more sense the way that you described it with the other explanation. I definitely see what you're saying. But in terms of taking this off of the ether list, nah, that's not it.
It doesn't support ether.
Yeah.
So why do you want it on your list?
It doesn't support your interpretation of it. This is a C plus V that produces a friendship pattern proportional to the velocity. And this was later patented, or technology was later patented based off of this to use an absolute frame to measure absolute velocity. So
well, the thing I keep stressing is that this paper literally cannot discriminate between C plus V or constant C.
Cool.
And
C
so
plus V is ether.
we cannot use it to disprove ether, and we cannot use it to disprove relativity. So it's not relevant to that discussion. It's a data point. It's useful. It's a fact of life.
Well,
but it doesn't discriminate.
Well, if it measures C plus V, then how did the Michelson-Morley should be 30? Then you can't explain any of that. Like
it does not measure C plus V. Once again, show me in this paper.
Right,
I'm going to ask you, if you can't do it, I'm going to ask you to please admit that you cannot do it.
I think we're done.
You're right. You're right. You're good.
No. You guys are just walking away to try to take a loss as a tie. It's not a tie. Y'all just lost, okay?
Look, I don't want to get into win or loss, dude.
It's not here.
It's not a win or loss. We're at a philosophical impasse.
Philosophical impasse.
It is not a philosophical impasse, you guys. Now look, show me in this paper where C plus V or C minus V is mentioned even once, and I will concede you're right.
Dude, we're back at the start of the circle, man. It's like we're in a ring laser gyro, just we're taking lots of readings over and over and over.
Well, explain to me this. It's philosophical difference then. In what way can you take a paper that literally does not mention C plus V and say that it is support of C plus V in your philosophy?
Because it's measuring velocity against the speed of light, which would only be possible through C plus V.
He's using Sagnac equations.
As the original Sagnac interpretation. It's pretty. Our position is pretty straightforward. So in your position,
if I work the math and show you the equations and show you that the C plus V is not in here, does that mean anything to you or not?
No, because you're just mechanismally interpreting what's producing the fringe differently.
So if you guys just declare that it's C plus V, that counts?
That's how it works. That's the variance. There's other supplemental evidence to support that we're just analyzing this paper right now.
I mean, you yourself admitted that that's the classical interpretation. So I don't understand why you can't. Why is it that sometimes you're okay with admitting that's the classical interpretation, but then it's like when we really want you to own that position, it's like you just won't own that position. It's odd.
Is that odd? I said it's the classical interpretation, yes. And I said over and over, you guys know what I mean when I say it cannot discriminate, right?
Yeah.
Then if it can't discriminate, then it's not a useful test. It's like I'm going to put 3 names in a hat, and then I'm going to roll a die, and if the die comes up 3, I say that I pulled out the name Fred, but that I didn't pull out the name Fred. I just rolled a die. That's not relevant. It's Why do you think that that's relevant?
We're talking in circles.
Yeah, I mean, I think we are. I think the paper does not support nor refute either position. That's what I'm saying. Do you guys agree with that?
If you want to hop out of the lab frame, you can claim whatever you want about this paper.
No, I'm staying in the lab frame. I'm staying firmly in the lab frame. And
so then you're gonna absorb the Lorentz transform to explain it. Then
there is no Lorentz transform needed. I've said that many
Sagnac effect in a
times.
relativistic framework, you have to absorb the Lorentz transform. Your own paper showed it. You either accept the classical framework of C plus V and C minus V, or you absorb the Lorentz transform.
It's very clear to me that you're absolutely not listening.
Yeah, maybe we should.
Can anybody else, maybe in the chat, back them up and tell me that I have not been clear on this? Please support these guys and explain to me that I have not been clear when I have shown. In fact, let me show. If you guys are willing to hang on for just a minute, let me show the paper. I will present the screen, and I want to show Tartaglia. This is the paper you're referring to. And note the C plus V, C minus V right there. Where's the Lorentz coming up, right? There. Here we go. Oh, he's doing the whole thing. Sagnac, okay, Sagnac without rotation. This is a relevant part. Is this the simple example? Is that where he talks about the Lorentz thing? Yep. I'm going to control F it. If you guys remember where it was.
Next page. There you go.
Okay, then we need a Lorentz transform between the blah, 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 right? This is what you're talking about.
Yep, you have to take the geometrically convenient position from the center and then do your Lorentz transform from there.
Okay. And then V much less than C. Okay, but did you also notice this? Consider that in all practical cases, we have V much less than C, and equation 1 will be transformed into the classical one. Do you see that? Let me make it bigger. This is the Lorentz one transformed into the classical, which does not have that term anymore. It's
gone. I understand that when you do the Lorentz transform, that you can remove the C plus V in that framework. I understand that. I'm saying
what I'm saying is that the Lorentz transform has been removed. The Lorentz transform has been removed. The whole Lorentz transform is gone.
Okay. So then we're back to.
This is just the classical.
Okay. So it's just you're refusing to. Okay. This is good. I've learned now even more why Dufour and Prunier is so relevant and why Wang proposed so many more variations of this experiment just a few years ago that would unequivocally. Yeah. Okay.
Yeah, we would have to go further. I mean, I don't know exactly what you're talking about, but it sounds like you're saying that Wang had to go to another experiment because this one didn't do it.
Although it's just weird because we would be in the reference frame of the Earth's motion in relation to the sun in that case, which is odd to me. So then we should be able to detect that linear motion.
We could if we could throw a fiber optic cable on the sun, right? Remembering, once again, the V we measure is the difference between the fiber optic cable and the racetrack. Okay,
so I would like to, I don't want to talk about another paper, but I would like to just look at one configuration and see if that would maybe show that we're all on the same page.
Okay.
Alan, do you remember when we ran into that configuration last night that had kind of a Dufour and Prunier, like it separated the reference frame.
Oh yeah. Let me see here.
Because I think if we could just agree about whether or not that would test this, then we can know that we're all on or not on the same page, you know?
Where was that new one? What year was that?
Like 2017 or something like that. I can't recall the exact year. It was his second most recent paper. My keyboard is not working for some reason.
Dang, I know I added it. Where did I add it? It was.
Yeah, while you guys are looking, I just want to show this again. I think we should be pretty clear at this point that the V we measure requires that the fiber optic cable be moving on a conveyor belt while the loop is not on that conveyor belt.
Do you have the paper too?
Right.
For it?
Right, Toby?
My
you're busy. You're busy.
Why my keyboard is being weird, Alan?
This one. Second. Nope.
Thanks for pulling it up, Alan.
Trying. We went. There were so many links last night.
Yeah, we did go through a lot last night.
Let's see. Nope.
You know what?
Nope, that's not it. No, I got it right here. Light
Okay,
Dragon Vacuum Tubes. It's by Ruyang Wang.
Yep. That's the one.
Cool. All right, let me screen share real quick.
Okay.
No, 11th chimp. I just happened to see that pop up on the screen. You're misunderstanding. What I'm trying to understand Matt's contention with Wang. It's not that this paper is making a different point. I want to get a clarification if this particular configuration, which is just a theoretical configuration, I want to get clarification if this configuration would satisfy him.
I think that's a really good idea.
Let me see here.
Alan, I don't think you're sharing at the moment.
Yeah, I'm trying to. 1 second, I have to download the paper.
While he's doing that, Toby, let me distract you for a second. This experiment, that if the fiber optic cable is not on a conveyor belt, it doesn't measure anything, right?
Without any velocity, yeah.
Okay, and if the racetrack was on the same conveyor belt, it would also measure nothing.
Without any motion?
No, if they move together, like we just put them on a truck, and the fiber optic cable and the loop all move together, we measure nothing.
That I'm not so sure on, because I mean that's exactly what his speedometer patent is kind of about.
Interesting. So it seems like, well, that's not this, right? So
yeah. So I'm just to answer your question. You asked me a question. I'm saying I don't know.
Okay, starting with just this one, from our understanding here,
I would assume actually that it would be picked up.
Interesting. So you think
I might not have. I wouldn't have been so sure about that before I saw the speedometer patent, and now I'm quite curious actually.
Okay, because this one, they did not do that.
What I understand that what's being measured here is in relation to the motion of the fiber. I understand that.
Right. So if you wanted to, like, say, measure Earth speed around the sun using something like this, we'd need, say, the Earth to be the conveyor belt, and then the sun would have to be the loop.
Yeah, and you're not. I get the difference there, because the reference is, it's actually a detached reference frame, right? Because it's not you'd have to take the fiber where the FOG is connected to the fiber there, and you'd have to somehow detach that, but still be able to measure that motion.
Yeah, well, you could do that. You can use just mirrors and stuff. Alan, take it.
Yeah, so I think, Matt, even regardless of our differences, I do think you'll find these configurations kind of cool and interesting. It's a pretty interesting paper. But in any case, so yeah, so here he's actually, you can take it away, Alan, if you want, since you're presenting. I don't know if you want me to try and explain.
No, I got you. Yeah. So what he's doing here is he's got the fiber setup that ends on a collimator that would like shoot a beam through the vacuum tube and then would recombine here. And basically, the only motion would be the vacuum tube.
Or so he's got a bunch of different
Or
configurations
no,
here to test.
no.
And then he's
Sorry,
going to move
I'm sorry.
he's going to move
I'm sorry.
the
Only the collimators will be moving. So the difference would be like the velocity of just the collimators right here, like moving this distance.
Well, I think what we've come to understand is that the space that light goes through, not the medium that it goes through, is what's relevant, right? And and I think that that was our big takeaway from the Wang and stuff.
Where was that?
So if he's changing the amount of physical space,
But he's not.
that
Right.
well, is he moving something or is he not moving something? I mean, probably an easier way to look at this, and something I find myself reflecting on is there a Doppler shift? If
Yep.
we pulsed the light and we just looked for a Doppler shift, would we read one? It's the same, right? The
How are
effect
you
should be the same.
measuring? How are you going to determine absolute space without some kind of frame of reference?
You need a frame of reference, yeah. Yeah, and that's the mind bender of special relativity. I'm not going to argue that it's not a mind bender. In special relativity, what's unique is that they say every inertial frame of reference
It's equally valid.
is equally valid. So, well, we don't need that in order to understand these experiments. We can just use the room we're in. We can just say the lab is a stationary frame of reference, and special relativity says we can. Classical relativity says we can. So no need to argue it. We're in the lab. Do the thing, and if you're moving the path that the path that the light goes through, if that moves, we should measure a Doppler shift. We should measure a fringe shift.
Okay, but we can't within all of this, we cannot walk away saying that C is constant unless we use a Lorentz transform.
The Lorentz transform isn't necessary for any of it.
Our measurement of C, just our perceptive, from our point of view, our lab frame.
Yeah.
Our measurement of C is going to be C plus V or C minus V. You can claim C is constant. That's fine. But you're going to have to use a transform. You're going to have to use a Lorentz transform to get out of the lab frame. You have to invoke something outside the lab frame.
In special relativity, you would have to, in order to keep C constant.
Yes,
in order
agreed,
for C to be constant in everybody's, yes, absolutely. I think I'm finally understanding you. In order to keep C constant in everybody's frame of reference, the only way that works is if there's a Lorentz transform.
Yes. Okay.
Yes, that is correct. That is absolutely correct. And under classical, you wouldn't have needed that.
Yep.
All right, man.
Okay, yeah, right here. Electroneutrino says Lorentz transform is only a way to convert between coordinate systems. It's all in the name. Yeah.
Yeah, and so me and Alan's position is that we don't want to be making assertions about the lab frame, our measured reality, based on coordinate system transforms that we can't verify.
I'm with you. I'm 110% with you. I'm so with you that I'm going to challenge your earlier statement with your current statement, which is I'm not going to make any assumptions about my lab frame, including assuming that it's an absolute frame of some kind. That is God's privileged frame. This is just my frame, and I'm not going to make any assumptions about it.
So
right?
Are you saying, okay, what is your
It's
point?
not God's frame, it's my frame.
Well, yeah, if I'm measuring from it, then my measurements are going to be relevant to that.
Right on. Absolutely right on.
Okay.
And in these experiments, the ones that we looked at, the takeaway here is that it doesn't matter how much glass the light goes through. It is how much space in my reference frame, how much of the lab reference frame space the light goes through determines how much fringe shift I get.
But the distance is the same. The only way you can invoke a change in the space is with referencing outside of your reference frame.
No, we're going to stay in our reference frame. We're not going any other reference frame. We moved the device during the experiment. So within my reference frame, the light had to start here and end here.
Okay.
So the light went through space in my reference frame, nobody else, just my reference frame. And it wasn't the glass, the length of the glass did not change, but I pulled the glass through a distance during the experiment.
Okay.
Right?
Yep.
And so there is no need to discuss special relativity one way or the other with this. It doesn't make any statements about it.
Yeah. I mean, I don't want to just keep repeating myself. So.
Okay. I mean, that's clearly what I'm doing. It seems like we agree that within the lab reference frame, it is not the distance of glass we go through. It is the distance of space within the lab reference frame that matters.
But I don't see how you can possibly invoke absolute space without a preferred frame.
I didn't invoke absolute space. I said lab space.
Lab space, so the preferred frame of the lab. If the distance of the fiber is the same, if the length of the fiber is the same, how are you making an assertion about space?
Lab space. The space within the lab.
Outside of the reference frame.
My reference frame. The lab's reference frame.
So you're making an assertion that space outside of your reference frame, the motion of that space somehow affected the speed of light.
No. I said that within my lab reference frame.
Yeah, but you're talking about the space being changed.
The space is just XYZ. It's just length. Space is just length. That's it. I don't mean like stars or anything. I just mean like
I know.
The volume, right? I moved the cable from here to here. It moved within my reference frame, no external reference frame.
Yep.
Agreed? It moved from here to here.
Yep.
And so the light had to go from here to here.
The distance didn't change though. It only moved relative to an absolute space.
It moved from here to here.
Relative to what?
From here to here. Relative to my face.
Which is in or outside of the lab frame?
In the lab frame.
Your face is in the lab frame?
Yes. I'm standing I'm in my room. I'm gonna reproduce the test right here.
You're not in the lab frame. The motion of the FOG on the conveyor in this particular configuration, you're not in the lab frame. You're outside of the lab frame making your measurements, right? Because you even the FOG is connected by the fiber.
Great. That's a good point. I am speaking as the lab person, as the experimenter. I am standing in the room.
Okay.
I am not a fog.
Yeah, you're not in the fog in that lab frame. You're outside of it, and your assertions about space are in a different lab frame than the moving fog.
Wait. What? I'm in my lab frame. There is only one lab frame. We're not going to leave the lab frame at any time.
The lab frame in this case is the experiment. It's the fog on the conveyor connected to the waveguide loop.
No. That's too confusing. I just want to stand on the floor with my hands on the table. I'm not moving. There's a conveyor belt in front of me on the table. It is moving. I am not.
So you're not in that reference frame.
I'm not in the same reference frame as the fiber optic cable might be considered to be.
And the fringe shift that's measured, which reference frame is that in?
All. It
Well,
can't be different.
when-
It can't be different in different reference
when the
frames.
measurement is taken, what reference frame is that measurement relevant to?
All reference frames.
Relation. What does that mean in this particular case?
It means if you take a picture in one reference frame, and then you take that picture into a different reference frame, well, we're really talking about reference frames wrong, but I think we understand each other. Take that to another reference, the picture does not change. The picture must be the same in all reference frames.
Okay, but I'm talking about when the picture got painted.
When the picture got painted, the picture must be the same in all reference frames.
The picture was painted in a particular reference frame. So you're looking at a painting from that reference frame. Maybe the painting analogy is not so good.
I think there's a fundamental misunderstanding about what a reference frame is. A reference frame is merely a coordinate system. It is an axis that we draw to work our math.
Yeah, okay.
You do not have to be physically attached to an object in order to be in a reference frame.
But when we're talking about motion and we're talking about measuring velocity of light, we're talking about a particular motion in a particular frame.
And
you are not in that motion. You are not in that motion with that frame.
I am a human.
And the absolute space that you're invoking is not in motion with that frame. It's outside of that frame. So you have to invoke an absolute space to even claim that there's a difference in length there.
No. I am going to work the entire problem as a human being standing in a room. I am not going to invoke any other reference frame.
But how would the light know about the room that you're in and about the absolute space that was changed in relation to its motion if it's still traveling the same length of cable?
I'm not claiming that it does.
So then how did we get a fringe shift?
I'm saying that because we get a fringe shift, we know that it is not the length of glass that matters. It is, in fact, the length of space that matters.
Okay.
Okay. Right? You agree with that, right?
I think we have a philosophical difference on this.
How can we have a difference on that?
It's okay.
I did not change the length
we have
of the
a
glass.
philosophical difference on this, right? Like, I think it's cool. We shouldn't all have the same point of view.
Well, we should definitely have different philosophical points of view. What we should do is agree. I think what we should do is agree with exactly what we just saw. What are the hard data points? And then interpret differently. I'm going to come away with an interpretation where C was constant and it was special relativity. And y'all are going to come away with, no, there's some preferred reference frame, but we just don't. This experiment just
we're gonna stick to classical framework. That's our contention is we don't want to step out of the lab frame. We're gonna stick to the classical framework. That's our position.
Yeah. You know what? And I'm doing that too right now. So there really shouldn't be an argument. I'm saying I'm just going to stick to the lab reference frame. I'm not going to invoke any other reference frame at all. Then what we see is that the fiber optic gyro, the gyro itself, moved during the experiment.
Yep. Showing
and we see that there is a direct linear relationship between that motion and the phase difference.
Yep. Somehow it's detecting absolute space. Isn't that interesting?
It's detecting lab space.
Which is only relevant to absolute space. The phase difference can only be measured relative to absolute space. You even said it as much as yourself.
I did use the word absolute space. And what I mean is lab space.
Mm-hmm.
And that was a bad word choice. I shouldn't have, because of this context, that's a really bad word choice. But see, I think from there, what we can hard agree is that in the lab space, motion turns into a fringe shift. And then you're making the philosophical reach that means lab space is absolute space.
Yeah, choosing not to go into relativistic explanations with different interpretations depending on the reference frame. Instead, I'm acknowledging, or I'm supposing a universal lab frame that we all exist within, and then a variance of C that's relative to our observations in the lab frame. The C is actually varying. Time and space are not warping around C.
Cool. And in that context, I'm with you. I'm totally with you. We're doing classical, absolutely. If we take this whole lab and we load it onto a truck, so that you and I agree now that this lab is moving, I'm going to step off the truck. So my reference frame is now the absolute reference frame we had from before. But this whole rig is going to drive past us at 100 miles an hour.
Okay.
If we just work the math, just classically, the light, the amount of space in the truck's reference frame is the same as it was in our lab reference frame. And if we translate that answer back to our reference frame, we once again see no fringe shift. Even in classical, this is not relativity at all. This is just classical dynamics, right?
That is your assertion.
And we can show that mathematically very easily because the light goes opposite directions. So at the one way it goes V plus C, the other way it goes V minus C.
Yep.
So when they meet up, the plus and the minus, they just subtract, right? They just one minus the other. That one's gone. I mean, maybe I could prepare some slides and show you the math on that. We've been going too long. I don't expect you guys want to see math right now.
We have been going for a while.
I don't think you want to see math right now. What I'm saying is,
30.
if you just do it, Newton's math, nobody else, you'll see that the speed of the lab that we put on the truck relative to ourselves cannot affect the fringe shift.
I mean, Wang's speedometer patent sure seems to indicate otherwise, but I understand that's not what we're talking about today.
Excellent. And if he's come up with something else, we should look at that. But I think the next step ought to be that I should do that math and show you those equations, let you look at those, and then you come back to me and tell me whether that's correct or not.
I mean, I don't really understand. I don't see the why that's a fruitful exercise. It's just kinematic equations. I don't disagree with kinematic equations that can explain things. Just like I said, I don't disagree that you could make a mathematical, and you could make a framework in which there are relativistic interpretations, and all of which they all are basically retrofitted around the constancy of C to make C constant. I don't dispute that. The math is there, and actually quite impressive math, right? I don't dispute that whatsoever.
Okay. So what are you disputing then?
Well, just with that particular assertion, talking about putting the interferometer on a car and driving across the country, I don't know about the experimental evidence for that, and especially when I see the speedometers that only uses interferometry to detect absolute speed through an absolute space, then I really have to wonder what where the rubber actually meets the road, so to say, on that particular example that you're invoking.
Okay. So yeah, Rachel's talking about what I was talking about there is that if we did it on a truck and it was identical, then wouldn't that imply that this particular experiment says nothing about absolute space?
Yeah, probably. Yeah, if you could, I'd have to look it over. I'd have to think about that a bit, but on its face, it does seem like absolute motion should. Yeah, it should be detectable.
Okay, so I mean, I'm happy to do that for this experiment, and I think you also need to show me if he's invented some way to detect absolute motion. Then you should show me that paper, because the paper we just looked at so far does not say that.
Cool.
There must be something more, right? And I keep encountering this. I look at one paper at a time. I don't see that in this paper.
Well, you're
another
never.
paper.
To be fair, and to be fair to you, and just honestly, maybe me and Alan should just concede at this point, because we've already hit the point where we're not going to really have, like, you're in a different philosophical framework than us, right? You're okay with warping everything around C. We're refusing to do that, so we're kind of at an impasse.
Well, I'll still show you the patent though, because it's cool.
Yeah,
I want you to see it, because
yeah.
I mean, like, I don't want to leave it unsubstantiated what we're saying, just like, you know, for the record or whatever. Like, I'll have it posted so you can make it available that people can see it. Like what we're saying is not like, we're not just making stuff up. Like, but anyway.
Excellent. And I think that's my philosophically, from a scientific standpoint, I'm happy to entertain either approach. I'm very open, mentally open to the classical approach and trying to figure out if there's a way to get ether to work. I was talking to Clive this morning about trying to make it work. And I'm very open to that. Where I keep getting stuck, and that I don't want to let this go, is the philosophy of how do we know? And when you guys come and tell me, oh yeah, I know there's an absolute reference frame, and I know that there's an east-west drift, and here's the paper that shows it, and that paper does not show that. That's what I'm talking about right now, is that it does not, right? And so we need to understand that, okay, that paper does not show that. We can see that paper does not show that. We move to the next paper that you think maybe shows that, right? And not just say, well, okay, it doesn't show it, but I still believe that it shows it.
That's not what I said.
That's not a philosophical difference. That's just something else.
That's not what I said.
Okay, so this paper makes no mention of C plus V, makes no mention of absolute reference frame or preferred reference frame. And if I can show you the math that shows that this paper can be done in any reference frame, then are you ready to concede that this paper does not support your position on its own?
My position, I mean, this just furthers my position. We can go back to just the Sagnac effect, and that alone solidifies my position.
Well, let's just agree to this paper, one paper at a time.
Well, we're already like multiple papers in, so that's why I kind of said, like, maybe we just have a philosophical impasse here, because I'm saying just the paper you sent about the Sagnac effect, either we have the classical interpretation C plus V, C minus V, awesome, or we use the Lorentz transform, unfalsifiable, unsubstantiated, unprovable. I don't like that.
Okay, you seem to have a philosophical wall that you hit when we say Lorentz transform. Even after we agree that we're not going to use the Lorentz transform.
The paper uses the Lorentz transform in order
and then
to have C be constant. See, if you want C to be constant, you have to. If you want C to be constant, you have to invoke the Lorentz transform. We just looked at the paper.
And I showed you where he discards
minus B, or.
And I showed you where he discards it. And you still won't read the rest of the paper or won't accept the results. It's amazing. Okay, we'll stick with this paper. The Wang paper does not mention Lorentz transform, I think, at all, right? So we can just work from that.
No, it's a classical framework.
Yeah. And so I just want you to say this paper in no way supports any assertions about a preferred framework or an absolute C.
But that is my interpretation. So,
but it doesn't actually support that. So how You're
That's
just
your assertion.
Your
invoking
interpretation
it.
doesn't support it. I'm not gonna subject myself to repeating that to capitulate to you to make you feel better, man. That's insane. Like, why would you ask us to do like what the fuck are you talking about, bro? It's a little overstepping, don't you think? We're at a philosophical impasse over the speed of light.
Okay. I mean, I'm sorry. I guess I'm being rude.
Yeah, what
I
the fuck are you talking
apologize.
about, man?
What am I talking about? Is that it literally does not say anything one way or the
No,
other.
no,
This has
no.
been my
You want
assertion the
us
whole
to make
time.
you feel better. Is that what we're
No,
here
I'm
for?
saying this paper does not say one way or the other. Whether
Then let's
there's a
leave it at our
conflict.
philosophical impasse then, and let's call it a day and stop trying to circle it back to this dog shit where you're like, yo, capitulate to what I'm saying, admit to this and that.
Okay.
Philosophical impasse,
Obviously,
bro.
it's gotten heated. Yeah. I did not my intention, but I'm not going to accept that a
I'm not asking you
reasonable
to accept
argument
it.
is
Fine.
I believe something and therefore it is so. Right?
It's your argument.
If an experiment, it's like Riley's famous egg experiment. You guys know the egg experiment? Like where you put salt in the water and it makes the egg float?
It a day?
Yeah, I think maybe we should call it a day. Maybe we can come back to this if you all are not too angry at me.
We'll be fine, man. We always get heated over a long conversation. We'll be all right, bro. But let's call it a day here before it gets any worse.
Okay, we're calling it a day. Thanks y'all for being here. Good to see you as always. Good to see you guys too. Yeah, I don't know how we can ever get past this philosophical impasse that you guys describe. If you have any ideas, that'd be great. I'll show you the math. You all can react. You can tell me what you think.
Cool.
Thanks, man. Appreciate it.
All right. Later on, people.
Thanks, Matt. Take care.
Bye.